So this is one of the more fun chapters of our course. It's on dark matter. It's something that I've also spent many years researching back in the good old days in the 90s with some pretty cool people like Joel Premack and Sandy Faber up at UC Santa Cruz. And so I know a fair amount about this. So let's begin. Dark matter. And don't ask me what it is yet, because we're going to leave that as a mystery. In fact, for maybe longer than you'd like, but anyway, that's what we're going to do. So the first evidence that dark matter might be out there, you could almost call it conceptual. You could ask, well, why should nature be so accommodating as to make everything easily accessible to our rather limited extent of eyeballs and even detectors? And so maybe there could be stuff out there that we don't know about. And there's this guy, a little unfortunate actually, Fritz Zwicky, who is a bit of a cranky guy, but also a very brilliant guy. Early in the 20th century, worked at Caltech, and he studied the Coma cluster. This is the richest large cluster of galaxies. It's much further away than the Virgo cluster, but it's also much richer. Virgo cluster is a pretty good cluster too, but it's about 1/3 of the distance, I think, as the Coma cluster. And the idea, there's the Coma cluster. These are the two giant cannibal galaxies that are in the middle of the Coma cluster. So these are merger products, just to do a little micro review. These are merger products of other galaxies. Probably 4, 5, 6, 7 different galaxies have all blurred together to make these two guys. Someday these two guys are probably going to wind up together and make a bigger guy in here. A couple of things to notice about the Virgo cluster. Look at how many ellipticals there are. Yeah, ellipticals are, among the bright galaxies, ellipticals are much less common than our spirals. But in rich clusters, collisions are more common, and so we get lots more merger products, and merger products, after they settle down, they become ellipticals. That's a star, not a galaxy. You can tell because of the four-pointed pattern there. That's diffraction around the secondary mirror support. Okay, so what he did with the Virgo cluster was he used the Mount Wilson telescope, the 100-inch Hooker telescope, and he measured the velocity that these galaxies were moving. So he took spectra, which is a very painstaking process on old glass plates back in the old days, and tried to find their absorption lines and then measure the Doppler effect, and so he could measure their velocities. Now the Coma cluster is pretty rich, and we're only seeing the inner part here. And when you zoom back and you look at the whole thing, you can tell that it is very concentrated in here, and the concentration of the cluster goes out. As you go out, goes less and less. And so the cluster looks what we say is dynamically relaxed, or at least it's gone a long ways towards that. So what that means is that each of the galaxies have probably been swung around in square dance fashion at least once or twice. And so the cluster has achieved a kind of relatively close steady state look to it. And that's important because what that means is that then you can measure the velocities and you can measure the size of the cluster, and that's going to tell you how much mass there must be to be swinging those galaxies around at the velocities that you see, and yet have those galaxies be spread out enough into the size that you see. So if you take Kepler's third law, and again I keep telling you that's the most valuable law in astronomy, it allows us to measure the masses of things. And if you take Kepler's third law and you do some statistics with it, we're not going to have elliptical orbits in a situation like this. We don't have a two-body situation. We have a 1,000-body or 2,000-body situation. But if you use Kepler's third law and you do some math with some statistics, then you can arrive at a reformulation that's called the virial theorem. And so one way to talk about this cluster is to say this cluster is virialized. The virial theorem. I think I might use this word later, but in case I don't, I'm going to write it out for you. Virial. Kind of like viral, but not. It's virial. The virial theorem. And the virial theorem is an easy relationship between the size, the average speed, and the squared velocity of the galaxies and the mass that's inside. And from the virial theorem, he calculated how much mass there was in this cluster. Then there's another way to figure out how much mass is in the cluster. You could just look at how bright these were, and you could look at the color of them, and thereby get an idea of their stellar population, knowing they're dominated by red giants, and having an idea of the mass of red giants and other stars. You get a statistical representation, decent guess of the stellar population, and you calculate how much mass there is in stars. Stars look like they're the dominant component of galaxies, and even if you throw in another factor of 50 or 70 or another maybe even 100% for hot gas that might be out there, you get an idea of how much mass there is in these clusters. And when he compared the two, he was amazed because they didn't match at all. The velocities of these galaxies was so fast that there must be, 10, 15, 100 times. I mean, it depends on the assumptions as to the distance, and he frankly didn't know the distance very well. But what you can say is that the mass was way more than you would get with just stars. So the idea of dark matter was born. But the problem was, this was Crazy Fritz who was telling us this, and it was way back in the 1930s. He was really way ahead of his time. And it wasn't that astronomers didn't believe him, because he had a reputation for being cranky and maybe a little rude sometimes, but he actually was a pretty smart fellow. But it was really before the time that we had enough technology to really check this out. So that knowledge just kind of sat there for a while. It sat there until we had new detectors that came along, and we had new astronomers come along, and so that's where we're going to go next. But anyway, this is just to give you time to read this slide here. You do have to admit that claiming that the Coma cluster has 10 times or even 160, depending on your assumptions, more mass than you can see is a pretty extraordinary claim for the 1930s. Extraordinary claims require extraordinary evidence. Sagan's corollary to Occam's razor, talked about in Chapter 0. So, what kind of extraordinary evidence could we possibly amass? Well, along comes Vera Rubin at the Carnegie Institute and her graduate students. And Vera Rubin, one of the top astronomers of the 20th century, she's just been honored with having her name put on one of the new space telescopes that's going out there. Oh my God! I think it's one of the space telescopes. Might be one of the new monster scopes that's going up. Anyway, the Vera Rubin telescope is going to be doing fantastic work, just like she did. And she came along with Kent Ford, and what they did is they measured the speed of the rotation of spiral galaxies. So the neat thing about spiral galaxies is that the stars all move in roughly circular orbits. And so you can get an idea of the mass that is inside that orbit by just using, again, a reformulation of Kepler's third law. Remember, one of the neat properties of gravity that we learned, and it's true in general relativity as well as in Newtonian gravity. And Newtonian gravity is just fine here for this purpose. We don't really need general relativity. But you get all the mass that's outside of your circular orbit in a spherically distributed mass pulls on you equally in all directions and therefore can be neglected. So what you get by mapping the velocity of stars that are at this distance, and then at this distance, and then at this distance, and then this distance, and so forth, and you just keep getting velocity measurements all the way out, and then you can get an idea of how much mass there is inside this orbit, and then that orbit, and then that orbit. And so what you get is what we call a rotation curve. And so that's what these curves are. So what would you expect if galaxies are what you see is what you get? So we're looking here at M33, the little dwarf galaxy, or not really dwarf, but kind of a middling spiral galaxy in our own local group. So of course it's pretty bright inside and it's pretty dense. There's a lot of stars. But if you forget about the black hole in the middle, which we already decided was scary, but also pretty minor in comparison to the total mass of the galaxy. So without loss of what I'm trying to get across here, we can just throw it away. Then if you look at orbits that are really in close, then you're encompassing almost no mass. So the velocity you'd expect would start out at 0, the rotation velocity, and then rapidly go up because you're encompassing more and more mass rapidly because there is so much density of stars in here. And then when you get about 2/3 of the way out, then you've pretty much reached a tipping point where now the amount of additional mass, the amount of additional stars that you're including as you go out further, is offset by the fact that you're getting farther away from it all. And when you get farther away from it all, then you know gravity gets weaker. So the generic rotation curve that you would expect, and that's what I'm leading up to, is this. You'd expect the rotation curve to rise rapidly, reach a peak, and then kind of gradually fall off. Now, it wouldn't fall off exactly like Kepler's law does in our solar system, because in our solar system, essentially all the mass is right at the center where the sun is. In the galaxy, it's much more distributed, even if you just think of the stars. But what was amazing that Vera Rubin found with spiral galaxies is that the rotation curve does not drop. In fact, for this particular galaxy, it continues to go up. And in all the galaxies that she looked at, it went up and then it either stayed flat or it continued to go up, and we did not see these falling rotation curves that we expected. So the general term that has kind of come to be used for this phenomenon is called flat rotation curves, because a lot of them look kind of flat. I think I might have a graph on that. Yeah, okay. So the disk, which is made up of mostly stars and gas and dust, shows the kind of curve that you'd expect. But the halo, the spherical component, never comes down. And the total does this. So this is telling us that, well, and then here's real data, old data, but good data. And again, and so Vera did this for a lot of spiral galaxies. And even though this was back in the 1970s, and yes, I'd like to think that astronomy was better than most fields in recognizing the, the brilliance of women. It was still lagging somewhat, and she then probably felt she had to work triply hard to get this good work totally recognized. So she did a lot of galaxies, is my point. She looked at a lot of spiral galaxies. She had good instrumentation, reticons and CCD chips later that could electronically measure the spectra much better than could glass plates, as we talked about in Chapter 6. And so she was able to get data that was hard to get before. And there you go, flat rotation curves. Okay, so that is indicating there is dark matter inside individual galaxies, as well as, according to Fritz Zwicky, inside these clusters of galaxies. So now, here in the 60s and 70s and later, we also had new access to new wavelengths. We had radio waves first, and then later we had X-ray telescopes that could go up. And so let's think about how we could measure the mass of a cluster of galaxies using these two phenomena. And even a third here, gravitational lensing. So let's think about X-rays. Okay, there is an X-ray picture of the Coma cluster. And that's the purple, so it's color-coded. Obviously, you can't see X-rays, so you have to color-code it. But what you're seeing here is dense and or hot, both kind of convolved together here to make more X-ray emission in the middle, and then any X-ray emission falls off as you go out. And you also see some X-ray emission concentrated around some of the brighter galaxies that are ellipticals, actually, if you look at their morphology. And now think about how that hot gas is going to distribute itself. Oh, so by the way, X-rays, it comes from gas that's of order 1,000,000 degrees. If you look at the velocities that Fritz Zwicky was measuring for the Coma cluster, the velocities were on the order of 1,000 kilometers per second. Pretty fast. If you plug that into our formula for 1/2 mv squared equals 3/2 kt, then you end up with a corresponding velocity. Well, the velocity of 1,000 kilometers per second gives you temperatures of order 1,000,000 degrees, and that's in the X-ray part of the spectrum. So you would expect if there was gas out there in this cluster, the gas is getting blended up by the blades of all these galaxies, moving through the cluster, stirring it up, heating it up to 1,000,000 degrees. Very thin gas, not super dense gas, but very thin, but still, that's pretty hot, and it's enough to give off X-rays. The extent of the X-rays and the temperature of the X-rays is a completely independent means to calculate how much mass there must be to heat up the gas to this level and have it extend out in this way. It's not really Kepler's third law. It's using a very different thing, but it's kind of related. You're again looking at temperature now as a proxy for velocity, essentially. But you're still using the size of the cluster as part of your diagnostic. Okay, now we're looking at another cluster of galaxies. This is not the Coma cluster. And now we're using a totally different technique, which we haven't talked about before. This is gravitational lensing. So we learned that one of the consequences and one of the demonstrations of the truth of Einstein's law of gravity was that light will bend when it goes through a gravitational field, and it will bend in the direction of the increase in gravitational mass. And so what that means is if you have a cluster, the foreground cluster here is all these fuzzy blobs of orange and yellow, and then the blue things are actually images of galaxies that are roughly twice as far away. Another cluster that's way in back. And what you want to notice is that the direction of these images, the orientation of these images, is showing a kind of, well, it's like looking through the bottom of a Coke bottle, okay? Coke bottle bottom effect. So these arcs, these gravitational lensed arcs, are all in the direction, the perpendicular to them goes towards the center of the gravitation that is causing the lensing. And by measuring the optics, you can essentially develop some laws of optics based on general relativity as to how background objects should be distorted as they go through this foreground gravitational field. And by using those laws of optics and inverting them, then you can figure out how much mass there has to be to cause that amount of lensing. That's the bottom line. Here's another cluster, and it's a little better resolution. And again, you see arcs and arcs and arcs everywhere. Those are all background galaxies that are being gravitationally lensed. Excuse me. So it's another way to get the mass. And it confirms what Zwicky was finding. It confirms what the X-rays are finding. It's confirming what Vera Rubin was finding, and it's beginning to look like pretty extraordinary evidence to back up a pretty extraordinary claim that the universe is dominated by something that we can't see. And so we have dark matter. There's dark matter in elliptical galaxies also. So how would you do that? Now remember what an elliptical galaxy is. It's really like a big swarm of bees, hundreds of billions of bees that are all buzzing around in a random way. So they're not going around in circular orbits, so you can't use Kepler's third law like you can with a spiral galaxy, but you can use, again, the virial theorem, a rewriting of the same basic physics, and figure out what is the mass in elliptical galaxies, and you can do that as you march outward through the galaxy. It's a little harder in ellipticals because their light falls off pretty rapidly. They don't drop off as conveniently gradually as does the light in a disk of stars like a spiral galaxy, but you can do it. Easier is using velocity dispersion. So what's the idea there? Well, if you lay your spectrograph slit across the image of a galaxy, okay, I was hoping I had a elliptical galaxy in the next slide, but I didn't. So you have to just imagine a big elliptical galaxy, and your slit has got some finite width inside your spectrograph, and it's laying across the image on the chip, the image of that galaxy, and it's going to let in the light of hundreds of millions of stars, not hundreds of billions like is in the total elliptical galaxy, but hundreds of millions anyway. And that's plenty enough to have a sampling of stars that are going towards you and away from you and sideways and every which way, because they're all moving randomly. Think about the way the Doppler effect is going to change the position of the spectral lines corresponding to each of those stars. Now you can't get a spectrum of one individual star in an elliptical galaxy because they're way too dim, but you are getting the collected light of all those hundreds of millions of stars. And so basically what's happening is the Doppler effect is smearing out across wavelength each of those spectral lines. So if you look at the H-alpha line, it doesn't look like a nice sharp line. It's 656.3 nanometers wavelength. It looks like a broad, blurry, smear of a line. Kind of like, instead of giving a nice fine pen line, you get more like the sideways swipe of an artist's soft, dark pencil of a line, and it's all spread out. And by measuring the width of those lines, you're measuring the Doppler broadening. You're measuring the velocities, the internal velocities inside that galaxy. And those velocities are caused by gravity, and the gravity is affected by the dark matter that's in that galaxy. So again, you can get the mass of elliptical galaxies by measuring its velocity dispersion. Probably worth remembering. The velocity dispersion. There's a buzzword for you. The width of the spectral lines. Now imagine that you could only get a blurry image of a really, really distant cluster of galaxies. Suppose your technology was so poor you couldn't even see individual galaxies. This isn't really true, but just imagine that were true. Then you could use exactly the same idea, Doppler broadening, measuring the width of spectral lines due to the collected light of all the galaxies in a cluster of galaxies. And the same idea would work. Luckily, we don't have to do that. We can see the individual galaxies, and then we can use the virial theorem